So once upon a time, long, long ago, when we were first talking about matrix arithmetic, I mentioned that we could take powers of matrices and add them together, and then we had polynomials of matrices, and we could even take power series of matrices. And so we're going to come back and look at that again now. So if we've got a square matrix, then we can define e to the at. So this is going to be the series from n equals 0 up to infinity. Actually, you know what? Let's go with k, because n is already used for the size of the matrix A. And then we just put in at for the argument in the power series. So we have this. And so what does this mean? Well, the 0th power is going to be the identity. And then we have at. And then we have 1/2 a squared t squared. And then we have 1 over 3 factorial a cubed t cubed, and so forth. And all of these things make sense. So the definition is I mean, it's comprehensible. So now look what happens when we apply the derivative to this matrix exponential. So then let's see. So we've got ddt, and I'm just going to grab this whole schmear that we had on the previous line and stick it right here. And so when we apply the derivative to this thing, well, the derivative of I, that's just a constant, so that's going to go away. And then we'll have, now the derivative operator is going to ignore this matrix right here, because it's a matrix of constants. So it's just going to attack the t. And so we'll get a. And then it's going to differentiate 1/2 t squared to become t in the next term, and so forth. And so now if we take this and we factor out the common factor of a out in front, then we have the identity plus at plus 1/2 a squared t squared, and you can see where this is going. We have a times e to the at. So curiously enough, this identity works just as well with matrices as it does with numbers, right? Okay, so now suppose that we've got x of t, and this is e to the at times some vector x naught, vector of constants. And so here, x naught, which you should think of then what we have is that if you look at x prime, this is e to the at x naught prime, which we just saw that derivative, that prime is going to ignore the vector of constants, and it's just going to hit the exponential. So it'll give us ae to the at, and the exponential, or sorry, and the x naught will be left alone. And so what does that tell you? Well, look what we just got. So the moral of the story then is that e to the at x naught solves x prime equals ax. Okay, so that's nothing short of miraculous, right? So putting this all together then, we've got a square n by n matrix, And we've got some vector of initial conditions. So we've got n initial conditions. Then the unique solution of the homogeneous equation with the specified initial conditions is going to be this one that we just cooked up. And for the non-homogeneous case, if B is some continuous vector valued function on the interval so this interval is some subset of the real line. If it's continuous on this interval, then the solution of the non-homogeneous equation is going to be given by variation of parameters. And in this form, it looks like x naught e to the at plus e to the at. So there's our fundamental matrix x times the integral, and then here we've got x inverse, and then we've got bs ds. And so there's good old variation of parameters. And so the most amazing thing just happened. After taking a differential equations course for 10 weeks, we now got back to the point where that very first problem that we ever did in this class, we can now solve with boldface letters and capital letters. And even the stuff that we did for solving linear first order equations comes back in boldface and capital 10 weeks later.